Great. All right. So yeah, how is the surface of the moon? Well, you'll see all along this presentation that the answer is obviously not unique. There is a variety of kind of surface on the moon, resulting of 4.5 billion years of evolution. But before answering this question, I would like to ask another one: why the age of the lunar surface is important, and why are we studying the moon? And one here we go. One of the first thing to mention is probably that the moon and the Earth share a common origin. 4.5 billion years ago, when the solar system just formed, planets were not in the same configuration than today, and the whole system was quite chaotic at the time, leading to a bunch of collisions between very large asteroids and planets orbiting around the sun at the time. And one of the collisions that took place about 4.5 billion years ago involved a body the size of Mars called Theia and the Earth. That's what you can see on the simulation showing the collision. And right after the impact, in about 100 years only, a bunch of debris in fusion started to orbit around the Earth and started to accrete, to agglomerate between each other to form the moon. And the thing is that on Earth, due to the plate tectonics, recycling, and the intense erosion of the crust, the clues of that collision are very hard to find, which is not the case on the moon. So basically, studying the moon equals pretty much to study the origin of the Earth and our own origin. And the interesting thing about the surface of the moon is that this layer is the witness of the geological processes that occurred since its formation. You have to imagine the moon as an onion composed by different layers: the core at the center, the mantle right above, and then the crust and the surface, which is the only surface we've got access with our technology. And all of these layers are in interaction between each other. And what you find on the surface of the moon in terms of the composition of the rocks, their age, and the features that shape the surface can give you a lot of information about what's happened and what is still happening in its interior, but also in space. So what's happened on the moon since its formation? Because we are looking at very long time scale, you can see on this figure a comparison between what's happened on Earth and on the moon over the last 4.5 billion years, with some marks focused on the emergence and the evolution of life on Earth. So on the moon, we believe that right after its formation, the crust was in fusion, forming what we call magma ocean. There have been a bunch of interactions between this magma ocean and the material that was just underneath. And after a couple of million years, the crust crystallized and the mantle and the core were what we call differentiated, separated in terms of composition a bit later. Then a couple of huge impacts formed all the dark area you can see when you observe the moon with the naked eyes. There are actually huge craters we call basins or mare that are composed of basalt. Pretty much the same basalt that you can see on Earth when you hike in a volcanic region. And all of this basalt was coming from the mantle thanks to all of the fractures created in the crust at the moment of the asteroid impact and filled up the cavity. So we do not have a clear idea about the frequency of these events for the reasons I will detail in the rest of the presentation. But we think that all of the mare were formed between about 4.2 and 3.9 billion years ago. But again, there is no current consensus about the precise timing of their formation. Okay, so now on the bottom left picture, you can see a field of hills or domes with 2 or 3 impact craters. If you do not see the domes at the background, you've got the top left picture to help you appreciate the relief. Actually, when you look at an image of the surface of the moon or Mars, it's quite hard to sometimes distinguish what is a cavity and what is a positive relief, because you do not have any familiar marks to help you like a tree or building. So all of the relief at the background are domes, and there are also a couple of impact craters at the bottom left. And actually, These domes are not mountains or hills, but volcanoes. And it's quite surprising, but the moon was marked by an intense period of volcanism that lasted no less than 1 or even 2 billion years. And this is during this period that lava came up from the mantle to form the mare of basalt. And obviously, all along this long history, the moon has been bombarded by billions of asteroids, leading the formation of impact craters like the crater Tycho that you can see on this picture. With a pair of binoculars, it's pretty easy to see it from a backyard with its characteristic rays. It's quite nice to see. And this crater was formed about 100 million years ago, which is quite young at a geological timescale. And actually, it's still the case at the moment. New craters are formed on the surface. They are tiny, and it doesn't happen so often, but it still happens today. And since about 3 billion years, we think that the majority of impact craters formed on the moon do not exceed 100 kilometers in size, and their frequency of formation is pretty constant over time. So I will detail this point right after, but as I said, before, it was not the case earlier, where a lot of large asteroids impacted the moon very often. So since a couple of minutes, I'm telling you what that this particular event on the moon happened 3 or 4 billion years ago. But how can we have access to this information? How do we actually date the surface of the moon and the geological events having shaped its surface? So basically, on Earth, when you do geology and you are interested about the evolution of a particular region, you go on the field, you collect some samples, some rocks, you bring them to the lab, and you can analyze their composition and their age with a bunch of cool instruments. And to determine their age, you can measure the amount of a particular isotope contained in your nice pebble, like the carbon-14, for instance. For all the rocks, we do not use the carbon-14 to date them, but we use other elements, other radiogenic isotopes. So here is how it works. At the moment of the formation of your rock, you've got a given amount of a particular atom. And this atom is not stable. It starts to disintegrate to give a daughter atom in red on the figure. And since we know the frequency of this transformation, by measuring the amount of daughter atoms we've got in the rock, we're able to estimate its age quite precisely. But the thing is that on the moon, you can't send a happy geologist every day to collect samples and bring them back on Earth. And unfortunately, we do not have so much samples from the moon. We do have lunar meteorites that were ejected from an impact with sufficient energy to eject a bunch of rocks from the surface and escape the lunar gravity. And some of these rocks have continued their course until the Earth, where they have been found on the ground. But the problem with meteorites is that we do not know where exactly they are coming from. What is the impact that ejected the rock from the surface? And it's quite tricky to study a rock without knowing the geological context where it has been collected. You know, it's a bit like if I gave you a rock I picked up in my garden, but you don't know where I live, and I am asking you to tell me about the geological history of the Earth. So it's quite tricky, right? You don't know if the rock is coming from Hawaii, from the Sahara, or from Antarctica. So it's quite tricky to interpret what you find inside the rock, and it's pretty much the same thing for lunar meteorites. And fortunately, the US sent astronauts on the surface of the moon, and the USSR sent some rovers between 69 and 76, and we've been able to bring back lunar samples. And for these samples, we have a geological context. You can see on the right the location of Apollo and Luna mission landing sites and where those rocks have been collected. So that's very good, but it's still very limited, right? For instance, we do not have any sample from the far side of the moon or from the southern hemisphere. So how can we get temporal information about features we do not have samples of? And we do that by using impact craters. So on this video, you can see all craters greater than 1 kilometer in diameter on the surface of the moon. And the colors represent the elevation of the surface, with in blue areas low elevation, and in red high elevation areas. And as you can see, there are thousands of craters of this size. And on the other video, you can see many more smaller craters. And actually, we estimate there are more than 1 million craters larger than 1 kilometer on the moon. And craters larger than 100 meters is ridiculously high, probably around 1 billion or more. So how can we use impact craters to date different surfaces on the moon? I told you before that the moon has been intensely bombarded by asteroids since its formation. So basically, an old surface would have accumulated more craters than a younger one. And that's basically what you can see on this video. And on these three pictures at the left, you've got a young surface with a few craters that has not been exposed for so long to the meteoritic bombardment. And at the right, you've got an older surface with larger craters, more numerous, that has been exposed to the bombardment for a longer period of time. So, okay, that's cool. With this logic, you can compare different surfaces with different number of craters, and we can tell which one is younger, which one is older. But we can't tell how old is the surface. 1 year old, 100 million years old, 4 billion years old? We don't know that, and we need something else to quantify that. So let's make a simple analogy. We're going to replace the moon surface by sidewalk and impact craters by chewing-gums. And now let's assume that a fresh sidewalk looks like that when it has just been built. And then people start walking on it, and because they are not very polite, they throw their chewing gum on the ground, and the number of chewing gum on the sidewalk, or the density of chewing gum, increases through time. Now, if you want to know the age of the sidewalk, you will have to know how many chewing gums are thrown on the floor per day or per year. In other words, you need the chewing gum throwing rate as you need the impact crating rate for the lunar surface to date its formation. And the good point is that we know that thanks to the samples that have been collected on the moon and dated in laboratory. We've been able to compare the number of impact craters located on the landing sites of those missions with the age of the rocks that have been collected. For example, here, this is the landing site of the Apollo 15, symbolized by the yellow star. And if you measure the size of each crater on the area around the place where the sample has been collected, like on this map with the blue circles, you obtain an histogram describing how many craters do you get on your surface for a given size of craters. That's what I show right here in blue, where the size of the craters are at the bottom of the plot, and the number of craters greater than a given size is shown at the right. So this is the results obtained from the Apollo 15 landing site. Now let's take the number of craters larger than 1 kilometer divided by the area of the surface you counted the craters, just for the reference. And that's what we call N1. And now you repeat the same measurements, but for all of the other landing sites for which we've got a sample. Basically, you get this plot showing the value N1, so the number of craters larger than 1 kilometer on the surface of each landing site versus the age of the corresponding rock. And you fit all the points with a curve that is shown in red here. And here we go. This is more or less your impact rate we were after. So that's cool. Actually, I would say it's actually the number of craters you would expect for any area of a given age. So you are able to convert a number of craters formed on any surface of the moon to an age. If you've got a telescope at home and a way to take a picture of the moon, you can try to measure the size of the craters on an area of the moon and derive its age. It's quite a good fun. But for this, you will have to count on an area formed pretty much at the same time everywhere, like a mare, for example. So this technique is quite powerful because if you use dynamical model to transpose the red curve I've shown you before on Mercury or on Mars, you will be able to date the geological events that have shaped their surface without visiting them, just by counting craters. And for instance, on the moon, you can see here Olympus Mons, the highest volcano in the solar system, and its caldera. And by counting the number of craters on the caldera, we can estimate the latest volcanic activity of the edifice at about 100 or 200 million years old, which is very recent. Or we can also estimate when and how long your liquid water has flown on the surface of Mars, which has important implication, obviously, on the research of life on the red planet. So you can see that the moon is very useful to study the other planets as well. However, the technique is not perfect. There are a lot of uncertainties and different models that have been proposed to link the cratering density with the age of the surface. So the main differences between these two models are the area mapped and counted for each landing site and some mathematical technique used to fit the curve to the measurements. And actually, if you've got the feeling that the difference here between the two models is negligible, it's not at all. For example, if I measure a cratering density of this value here at the left, I will obtain 3.3 billion years old for the age of the surface using the red model, and 2.5 billion years old with the blue model. So the differences can be huge. And actually, this technique is very good to give an idea of the age of the surface, but the values obtained cannot be interpreted as a face value. It's just a model. And there is also an important thing to consider when you use this technique, the secondary craters. These kind of craters are not formed directly from an asteroid impact. Actually, what's happened when you hit the surface at 10 or 20 kilometers per second is that the energy involved in the impact is so high that a large portion of the impacted material is excavated and spread all around the crater, forming what we call an ejecta curtain. And some of the debris are big enough to form a secondary crater when they re-impact the surface. So that's what you can see on the bottom right figure in orange, where you get a lot of elliptical craters in chains. So now we can, what can we do to further improve this technique? One of the things that makes this technique difficult to apply on the wall surface is the increasing number of craters with the decreasing of the size. I told you at the beginning there were 1 million craters larger than 1 kilometer on the moon, and there are probably more than 1 billion larger than 100 meters. And this trend is coming from the size distribution of the impactors creating these craters. The main source of impactors is the main asteroid belt, and when you measure the size of the asteroids in the belts using a telescope, you see exactly the same trend, with a few large asteroids and a bunch of small ones. And this is the same thing when you crunch a rusk. That's exactly the same process. You get 1 or 2 large pieces and a bunch of tiny crumbs you spend hours to clean up after the breakfast of your kids. See, this is the same story. So to be able to map all of these tiny craters, you can use artificial intelligence to help you identifying and measuring them in a timely fashion. on the whole surface of the moon. And that's what our group is basically doing since about 3 years. What you have to do is to compare where the craters are on an image, and you're learning how to recognize them. So we've done that for the moon and even on Mars, where our algorithm has been able to count more than 90 million craters down to about 50 meters in diameter on the whole surface of Mars. So the figure on the right is showing you the distribution of the craters close to Olympus Mons, the highest volcano in the solar system. And you can see on this map, there are a couple of radial structures coming from a single point. And these radial structures are actually 1 million secondary craters formed following the formation of a 30-kilometer crater on the surface. So actually, this kind of technique can also help to identify where secondary craters are formed and improve the technique of crater counting. So it's quite interesting as well. But the best improvement ever, without doubt, will be to collect more samples at different locations on the moon. If I go back to this diagram, you can see there is any point, any samples between 3 billion years and 1 billion years, as well as beyond 3.8 billion years. We do not have any samples older than 3.8 billion years from the moon. And this is one of the most important gaps to fill in planetary science that will help us to better constrain the models and improve the measurement of the age of the surface on the moon, but also on Mars. And actually, people started to do so no later than last year when the Chinese mission Chang'e 5 landed on the surface of the moon and collected some samples that are going to be analyzed this summer. The landing site is located very close to the Mons Franker. This is a volcanic edifice considered as the youngest on the surface. So a lot of amazing results are coming soon, so stay tuned. We're gonna see amazing results very soon for this mission. And finally, the Artemis mission, obviously, that planned to go back on the moon in the next couple of years, that will allow to know a bit more about the early story of our satellite. So as far as I know, the landing site is not decided yet, but there is a good chance that this manned mission will land on the South Pole Aitken basin, which is the largest and the oldest basin on the moon. So a lot of things will happen very soon on the moon. But I think I'm done. This is a couple of resources and credits if you want to dig a bit more on this topic. And I'm happy to answer to a couple of questions. Thank you.
Thank you